Testing, can you hear me? Okay, this video is public now, so I'm going to be reading about computer architecture again, and just going to continue from where I left off last time. So last time I was learning about the ARM assembly language, and yeah, I saw some examples like this add, subtract, and then reverse subtract. I think there was some, yeah, move not. So move not, like it does not first on the source immediate register and then moves the result to the destination register. And then I learned about multiply. So there are logical operations and XOR, exclusive or yeah, normal OR and bit clear. And then there was the multiplication, then arithmetic. So R1, R2, R3, R4. So R2 and R3 will multiply. Then add with R4 and the result will be stored in R1. We have SMUL and UMUL. SMUL is signed multiply and UMUL is unsigned. These two, like if there's an overflow in the result, they will just truncate the overflow. But then SMUL and UMUL, they perform signed and unsigned multiplication. But R1 will store the lower 32 bits and R0 will store the upper 32 bits. Sorry, it's the other way. Wait. R0 will store the lower 32 bits and R1 will store the upper 32 bits. Yeah. Yeah. Then we have S divide and signed divide and unsigned divide. And then they do the division and return the quotient. And then we have the shift operator. So there's logical shift left, logical shift right, arithmetic shift right, and rotate right. So yeah, if I have one, 1001101. Perhaps something like this. If I do logical shift left, all the bits will be shifted left by 1. This will be deleted. Actually, no, sorry. Left that side. All of them will be shifted 1 unit. The overflow will disappear. And then we have 1, 2, 3, 4, 1, 2, 3. Yeah, we end up with this. Yeah. And then if we have logical shift right, so let's say this is the original. Logical shift left shifts all the value to the left. Logical shift right shifts all the value to the right. So I have 1 0, so 1 0 0. 1 0 and then 0 over here. And then I have arithmetic shift right. Arithmetic shift right. I think it shifts to the right, but it adds 1. First part, arithmetic shift right. It adds what the previous value contains. Like the most significant, instead of a 0 here, it will be whatever was contained here. So it will shift right normally. Then instead of 0 here, it will be 1. That's arithmetic shift right. So it will contain the bit that was previously stored. And then finally, we have rotate right. Rotate right. So it rotates, revolves it. We 1 0 0 1 1 1 0 1. This one goes at the end. Whatever is stored over here goes at the end. So now we have 1 1 0. And then so when we are making an instruction, we can write the instruction over here, like add, multiply, whatever. Destination, register operand 1 and then operand 2. Operand 2 could be another register. It can be an immediate or it can be one of those shift operators. Let me see if this works in the simulator. So I found this simulator online. I don't know how well it works. So move R0 and then we will store 3. Then move R1, what is stored in R0, but left shift by 2 values. And format should be decimal unsigned. Compile succeeded. Step over 3, 12. When we do left shift, it multiplies by 2, right? So 3 times 2 is 6, and then times 2 again is 12. Yeah. And then it ends. We have now seen different formats of operands. An operand can either be a register, an immediate, or a shifted register. We have up till now seen 3 addressing modes. So register addressing, where we address the register. Immediate addressing, like when we do one, like like uh, like over here, R1, R15, R5 to R1, and then shift addressing. ARM has four compare instructions: compare, compare not, test, and test equal in a two address format. These instructions compare the values in the two registers and save some properties of the result of the comparison in a dedicated register called CPSR register. Other instructions base their behavior on the value saved in the CPRS register. This is similar to flag register and simple RISC. So wait, we have is CPSR in here in the 15 registers, 16, right? 16 registers. There are two sets of instructions that can set CPSR flags. The first set compromises compare instructions. Second set includes flag setting variants of generic instructions. In other case, the rules for setting the flags are as follows. Negative, this flag is set if the result is a 2's complement base signed integer. It is set to 1 if the result is negative and 0 if it is non-negative. This flag is set if the result is a 2's complement base signed integer. Okay, if it's a negative. So negative flag, and then we have the 0 flag. This flag is set to 0 if the result is 0. Carry flag, for an addition, the C bit is set to 1 if the result produces a carry. This can happen when there was an overflow while adding the unsigned numbers. For example, we add this -1 and -2, and the result is -3. There is a carry out at the most significant bit. Not that there is no real overflow because -3 can be represented in the number system. However, if the numbers are treated as unsigned numbers, then there is an unsigned overflow. Uh, for a subtraction, the carry bit is set to 0 if there is an unsigned underflow. Okay. Overflow V is set to 1. It for logical operation, C is equal to the last bit shifted out. So V overflow V is set to 1 when an actual signed overflow or underflow occurs. Now that in the rest of the book, you might casually refer to both underflow and overflow and underflow as overflow. ARM has four compare instructions: compare, compare not, test, and TST in T equal. All four of them update the CPSR flags. Let us consider the compare instructions. So where are these flags stored? Are they inside the CPU? Like a separate register? Four bits that it stores on position 29 to 32. It is a 32. So current program status register is a 32-bit register like other registers and is usually used implicitly. In this book, we are concerned with 4 bits that it stores in the position 29 to 32. Compare, compare not, TST, T equal. Let us consider the compare instruction. It is a two address instruction that takes two inputs. It essentially subtracts their values and sets the appropriate flags. For example, if the values are equal, then the 0 flag is set. Data instructions can take some decisions based on these flags. For example, they might decide if they need to branch or perform a certain computation based on the value of the zero flag. We show the semantics of all four compare instructions. Compare set flags after computing R1 minus R2. Compare not set flag after computing R1 plus R2. When is CMP actually compare or is it something else? So TST set flags after computing R1 and R2. And T equals set flags after computing R1 XOR R2. Compare computes the flag after adding the register values. TST computes bitwise OR of the two operands and then sets the flag. T equals test for equality by computing an XOR of the operands. Normal instructions such as add and sub do not set the CPSR flag. However, it is possible to make any data processing instruction set the flags by adding the suffix s to it. For example, add s and sub s. Instructions do the regular job of addition and subtraction respectively, and additionally also set the CPSR flags. The rules for setting the flags are given in section 4.2.3. So they're talking about this section. There are three simple data processing instructions that use the CPSR flags in their computation. And they are SPS, RSC, and ADC. Let us now motivate this section with an example. Our basic ARM instruction format does not support 64-bit registers. Consequently, if we desire to implement the long data type that uses 64 bits, we need to use two registers. Let us assume that one long value is present in registers R2 and R1. Here R2 contains the upper 32 bits and R1 contains the lower 32 bits. Let the second long value be present in registers R4 and R3. Let us now try to add these two long values to produce a 64-bit result and save it in registers R6 and R5. Add two long values stored in R2, R1 and R4, R3. Stored in where? The add as instruction adds the values R1 and R3. I think this is adding the lower 32 bits. This is adding the upper 32 bits. So the add as instruction adds the values in R1 and R3. Add C add with carry. Okay, so add with carry adds R2 and R4 and the value of the carry flag. Okay, I see. So what is the S flag called again? Oops. Hold on. What is the S flag called? SPSR, current program status register. Okay, what is the S suffix called? We list the semantics of the instructions in table 4.8. Note that in the case of a subtraction, the carry flag is set to 0 when there is a borrow. The NOT operation flips is 0 to 1 and vice versa. Lastly, RCS stands for reverse subtract with carry. R2 minus R3 minus naught. In reverse subtraction, R3 minus R2 minus naught. Subtraction with carry, reverse subtraction with carry. And then this is add with carry. And then add S and sub S. Set the CPSR flags. CPSR status register, current program status registers. Simple branch instructions and ISA with just data processing instructions is very weak. We need branch instructions so that we can implement if statements and for loops. ARM programs primarily use three branch instructions to do most of their work. They are B equal, B not equal. So B jump to a label, B equal, jump if the Z flag is 1, B not equal, jump if the Z flag is 0. And then the Z flag. Z is the 0 flag. When we do compare and they're equal, that will set the Z flag to 1, right? And an ARM assembly program to compute the factorial of a positive number, store it in R0, save the result in R1. Okay, I did this with simple disk. Let us now see how we can use the power of branches to write some powerful programs. It is considered a factorial function. Example 44, we show a small program to compute the factorial of a number R3 is a counter that is initialized to 0. Keep on incrementing it till it matches R0. R1 represents the product. Iteratively multiply the value of R3 with R1 at the end of the set of iterations. R1 contains the factorial of the value given in R0. Write an assembly program to find out if a natural number stored in R0 is a perfect square. Save the Boolean result in R1. Is a perfect square. Okay. Stored in R0. So let's say R0 stores 25. We can keep multiplying. Okay, so if R1 is set to 1, then it has ended. Okay, so what we can do, we can keep multiplying. Let's say 25 is stored in R0. Let's just do this R5. Okay. Can I move to R1, 1. I'll call this func. Move R1, 1. No. Not move R1, 1. Start here. How do we show the result though? Save the Boolean result in R1. Okay, we save it in R1. We start with 1. We multiply R1 with itself. Save it in R2. Actually, R2, R3. We multiply it. Save it in R3. And we compare it with what's stored in R1. Compare. Um, R2, R2 multiply R3, compare R3, R0. Branch if equal to true. How do you check greater than? How do you do branch if greater than? So R2 times R2 is stored in R3 and then add R2, R2. So increment R2 by 1. Increment R2 by 1. Next R3 will contain 2 times 2 and then in the next loop R3 will contain 3 times 3 and then the next loop R3 will contain 4 times 4 and so on. But how long do we do this for? Branch if equal to true. I think we can subtract it. We can subtract R0. So subtract S. Do the regular job. Also set the CPSR flags. R1 minus R3. R3 stores the square, right? If the square number in R3 is more than R0, so 25 minus 1 and then 25 minus 4 and then 25 minus 9. Store it over here. But if there is an overflow, It's not clear what sub S does. Sub S subtracts the value of R3 from the value in R1. R3 minus R1 subtracts the value in R4 from the value in R2. R is 25 minus 1 and then 25 minus 4 and then 25 minus 9 and then minus 16 minus 25. Let's say this was 26. Then 36 minus 20. No. 26 minus 36. There's an underflow. So how do we branch in that case? R2 with 0. Compare R2 with R0. So 2 times 2. Store it in R3 and then my internet is fluctuating really badly. So anyways, R3, 1 times 1, store it in R3. Compare and then branch if equal. That's what I did. I just write it square. And then increment, okay. I did the incrementing. But then we are comparing it with R0 though, why? I think it's a very inefficient. Maybe if I learn other algorithms, it would make sense. R2, R0. Branch if equal, right? Branch not equal. Yeah, that makes sense. Branch not equal. Dot loop. But if it is equal, branch if equal and otherwise branch to dot loop. What this algorithm is doing is like there's a counter, let's say 1 times 1 is 1. Then the counter increments 2 times 2 is 4. Let's say R0 stores 25 and then the counter increments. This is what? Is R3, right? 3 times 3 is 9. 4, 16. Let's say R0 stores 26 and then 5, 25. The loop will keep happening. If it were to be equal, R3 and R0, if they're equal, then it will go to true, it will go to square. It will go to square, which will set R1 to 1. Otherwise, it will keep looping. It will just keep on looping until R2 becomes equal to R0, and then it will exit the loop. But I think we should just end it after 5, no? Instead of comparing this, we should compare this when this gets greater than R0. We can use simple branch instructions to implement for and if. However, we need stronger variants of the branch instructions to implement function calls. Function calls are different from regular branches because we need to remember the point in the program that the function needs to return to. ARM provides the branch and link instruction for this purpose. The semantics of this instruction is shown in table 4.10. So jump unconditionally to the function at foo, save the next PC in the LR register. The BL instruction jumps to the function that begins at the specified label. Note that in the ARM ISA, there's no special way for designating the start of a function. Now, what is this though? Any instruction in principle can be the start of a function. In ARM assembly, the starting instruction of a function needs to have a label assigned to it. Along with branching to a given label, the BL instruction also saves the value of the return address. It is equal to the current PC plus 4 into the LR register, R14. Event 12, 13, 14. Okay. I'm going to see a usage of this. Once a function starts executing, it is expected that it will preserve the value of the return address saved in the LR register unless it invokes other functions. If a value invokes other functions, it needs to spill and restore registers as mentioned in section 3.3.10. When we wish to return from a function, we need to move in the LR register to the PC register, R15. The PC will point to the instruction of the return address and execution will proceed from that point. So to int x plus 3, y is equal to x plus 4. So main is over here. Move 3 to R1. Branch foo. Branch to foo. Move 2 to R0. And move LR to PC. So PC contains main, right? The PC will point to the instruction of the return address. We need to add 4 over here because the size of an instruction in ARM is exactly equal to the 4 bytes. So if we take 4 and add 4 to it, it will then point to main, right? Because right after 4, it's main. Main is the next address after foo. Then add R2, R0, R1. Wait, hold on, can I copy this? Foo, main. Wait, this is 0. 0, now let's try. Uh, step over 2. Wait, no, 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 no. I think this makes more sense. Branch to end. Step over 2. Branch to extend. To 3 and then 3 plus. So the result is stored in R2. Wait, I want to start again. 0, 0, 0. PC, yeah, restart. So first 3 is to, why 3? Invoke foo. Pair foo. Step over. Let's restart. Step into foo. Yeah, you store 3 in R1 and then we move to 2, store it here, and then foo is extend, right? And then 14 is stored here. PCLR 8, 18. Hold on, I just want to see branch. Wait. Branch main is hexadecimal 4. Okay. So step into, okay, so PC contains 4. 4 is the next instruction. Now we have R1 3, store 3 to R1. Then branch to 4, 40, branch to 14. Okay. Then R0 stores 2. And then next Next instruction is the one stored in LR, right? Which is this over here. Instruction C, instruction address C. So branch 4, address 4. Branch L goes to foo, goes to 14, but it stores in the link register C, right? That's what branch L does. And then the result is stored in R2. In the equivalent ARM code, we define two labels. Okay, yeah. Nowadays, a simpler method is used to return from a function. We can use the bx instruction that jumps to an address contained in a register. Jump unconditionally to add to the address contained in register R2. So move R3 to here. BL4, jump unconditionally to LR. Now we have a very good idea of basic branch instructions. Let us elaborate some special features of ARM assembly. These features help make the process of coding very efficient. Let us consider the instructions B equal, B not equal again. We note that they are variants of the basic B instruction. They are distinguished by their suffix. Format denotes equality. These suffixes are known as condition codes. So condition codes in 4.12, there are 16 condition codes. Equal, not equal, carry set, reserved, flag state. So it checks for these states, right? Equal, not equal, C1, carry clear, minus, positive, plus, overflow, no overflow. As described in section 4.2.3, if a subtraction of unsigned numbers leads to a borrow, then the carry flag is set to 0. Condition is also known as unsigned or underflow. If there is no borrow, then the carry flag is set to 1. Kacha can leave the comparison between unsigned numbers concludes that the first number is greater than or equal to the second number, then the carry flag needs to be set to 1. Likewise, if the carry flag is set to 0, then we can say that the first operand is smaller than the second operand. These two conditions are captured by the HS and LO condition codes respectively. HS and LO. The next two condition codes check if a number is positive or negative. If there has been an overflow, these conditions can be trivially evaluated by considering the values of negative and overflow flags respectively. HI denotes unsigned higher. In this case, we need to additionally test the Z flag. Likewise, for LS, we need to test the Z flag along with the C flag. ARM has 4 condition codes for assigned numbers. Greater than, less than, greater than or equal to, less than or equal to, greater than, and less than. The greater or equal to condition code simply tests the end flag. It should be equal to 0. This means that the preceding compare or sub as instruction has subtracted 2 numbers, where the first operand was greater than or equal to the second operand. And that was signed numbers, we have not considered the possibility of an overflow in table 1.12, 4.12. Theorem 2.3.4.1 outlines the precise conditions for detecting an overflow. We leave the process of augmenting the conditions to consider overflow as an exercise for the reader. Lastly, the AL condition code means that the instruction is not associated with any condition. It executes according to the default specification. What's the point of even specifying this? Condition codes are not restricted to branches. You can use condition codes with normal instructions such as add and sub also. For example, the instruction add equal performs an additional in addition if the z flag in the flag s register is set to 2. It means that the last time that the flags were set, the instruction must have concluded an equality. However, if the last comparison instruction concluded that its operand are unequal, then the ARM processor treats add equal instruction as a no instruction. We shall see in chapter 10 that by using such conditional instructions, we can improve the performance of an advanced processor. Write a program in RSMD to count the number of ones in a 32-bit number stored in R1. Save the result in R4. So 32 stored in R1. Index count. So we do and R3, R1. So okay, we are extracting the least significant bit. Compare R3 and 1. Okay. Compare R3 and 1. The least significant bit is 0. Then now what is compare? The flag. What are the flags are compare? Which flag does this set? Okay, wait. So it compares if they're equal, then increment R4. They're not equal, do nothing. And then we do right shift, logical shift right by 1 unit. Then add R2 with R2. Loop condition. Or compare R2. Oh, this is we are checking if we have crossed 32 bits. Compare R2 with 32. If this is true, then branch. Okay, branch if R2 is less than 32. Otherwise, we keep going. The simplest load and store instructions are LDR and STR. Load to register and store to register, respectively. Here is an example. LDR R1 R0. This instruction directs the processor to load the value in register R1 from the memory location stored in R0. Memory location stored in R0 and then get it, store it in R1. How does this implement? This is the main memory. Hold on, let me see. Move to R0, value 3, and then store. Want to see how the store instruction works. You can specify load and store instruction with a base register and an optional offset. Oh, this is how arrays are made. Here the memory address is equal to the value in R0 plus 4. Also, we can specify a register inside. The memory address is R0 plus R2. So store. Okay, okay, I have an idea. Store. Um, let's say we store one over here. No. Register R1 has value one, and then we store the value store in R0 to the memory address stored in R1. No. Let's see what this does. So R0 becomes R3. Yes, and then R1 set it. Yes. Not about this store. Memory write of 4 bytes at address 1 is misaligned. Memory write of 4 bytes at address 1 is misaligned. Okay, I don't understand this. What is this SND over here? Okay, move to R0 this value. Move to R1 this value. Store in R0. Store what is stored in R0 to the memory address in R1. Instruction fetch from a location outside of a code section. Table 4.13 shows the semantics of different types of load store instructions. The third column shows the addressing mode. The register R2 in this case is known as the index register. Want to see an example of load store? Load store instructions load store 4 bytes of data. However, it is possible to write and store 1 or 2 bytes. 2 bytes is also known as a half word, where a word is equal to 4 bytes. So 1 unsigned byte, half, 2 unsigned byte. Store 1 unsigned byte. Okay, let's store 1 byte. Step, step, step. Like, what is this over here? What's happening here? Inside the code section. Is it like this? Yes, it is. I think they don't allow. Yet, at a good point to take a look at some advanced features and the ARM instruction set. Up until now, we have taken a look at the basic instructions that allow us to implement simple data types in a high-level language such as C or Java. We can translate simple programs to contain integers into assembly code and compute the results of some mathematical functions, load and store values from memory. However, there are other high-level functions such as functions, arrays, structures that are present in high-level languages. Okay, let's see. Note that the starting memory location of entry I is equal to the base address of the array plus 4i. This is okay in an array with a word size element. High-level language, the programmer always specifies the index and relies on the compiler to multiply the index by 4. ARM assembly provides nice features to multiply I by 4 by using L shift L instruction. This feature can be embedded in load store instructions. In this case, the base instruction is stored in register R1, offset is R2, and then left shift 2. Convert the following C program to ARM assembly. Assume that the base address of the array is stored in R0. Index sum. R1 stores the sum, R2 stores the index, R3 base address of the array A is stored in address R0. R2 is the offset. Left shift 2. You're loading this address, right? Why are we doing this? Oh no, R2 is 0, so this wouldn't matter. So anyways, increment the index. R1, R1, R3. So sum R3, sum what is stored in the array A0, R3 is 0 right now, and then R2 is not equal to this, then loop. Why is this? Oh, there are 100 elements. Okay, yeah. Wait, there are 100. Okay, yeah. And when we increment R2, we are skipping over 4 bytes, right? I mean, skipping over a word. Yeah, 4 bytes. Yeah, that makes sense. There is a scope for added efficiency here. We know that line 6 and 7 form a standard pattern. Line 6 reads the array entry and line 7 increments the index. Almost all sequential array accesses follow a similar pattern. The ARM architecture adds two extra addressing modes for the load and store instructions to achieve this. They are called pre-indexed and post-indexed with auto-update. The pre-index addressing mode with auto-update, the base address is updated first, and then the effective memory address is computed. The post-index scheme, the base address is updated after the effective address is computed. The pre-index addressing mode with auto-update is implemented by adding an exclamation sign after the index. So let's see what they're doing. So if I have an exclamation mark, R3 will load from R0 plus 4, but then R0 will increment to 4, right? And then with the second one, R3 will store R0 plus R1 shifted by 2, and then that gets stored in R0. The post index addressing mode is implemented by encapsulating the base address within the square brackets and writing the offset argument separated by comma after it. So R3, R0, and then this is the same example. So we load what is stored in R0 to R3, but we add 4 every time after the loading is done. And we compare R0 to, okay, so R4 stores the end of the array. Implementing structures is very similar to implementing arrays. Let's look at a typical structure in C. You can treat each structure as an array. Consequently, a structure will have a base address and each element of the structure will have an offset. Unlike an array, different elements in a structure can have different sizes. Thus, they are not constrained to start with offsets that are multiples of the word size. Offset 0, 4, 8, 10, 12. Table 4.15 shows the offsets for different elements within a structure. We need to note that compilers for the ARM architecture impose additional constraints. Okay, let us now use two sophisticated ARM instructions for spinning and restoring registers in the stack. They can be used to implement both caller saved and callee saved functions. Let us now describe two instructions to use the stack for saving and restoring a set of registers. These registers load and store multiple registers in a memory region such as the stack. So what does the FD stand for? Load from memory, I'm guessing something. For brevity, we do not consider generic memory regions in this book. We limit our discussion to the stack. So they take a base register, set of registers as argument. They load or store the set of registers in the memory region pointed to by the base register. Note that the order of the registers do not matter. The registers are always rearranged in ascending order. Let us consider an example using the store instruction stmfd. So load multiple FD. What is FD? So pop the stack and assign values to register in ascending orders. Update the value of SP. Okay, I need to see an example of this. Push the registers on the stack in descending order. Update the value of SP. The store memory FD instruction assumes a downward going stack, and it also assumes that the stack pointer points to the starting address of the value at the top of the stack. Recall at the top of the stack in a downward growing stack is defined as the starting address of the last value pushed on the stack. In this case, the registers are processed in ascending order: R1, R2, R3, R4. Secondly, memory addresses are also accessed in ascending order. Consequently, R1 will be saved in SP minus 16, R2 will be saved in SP minus 12, R3 will be saved in SP minus 8. And this is the SP. Alternatively, we can explain this instruction by observing that registers are pushed into the stack in descending order. Use the suffix exclamation mark with the base address register to instruct the processor to update the value of the stack pointer after the execution of the instruction. In this case, we set SP equal to SP minus 16. There's a variant of this instruction that does not set the stack pointer to the starting memory, to the starting address of the memory region used to save register. Example with this variant is this. Know that this variant is rarely used in practice, especially when the base register is SP. Similarly, load MFD instruction loads a set of values starting at the stack pointer and updates the stack pointer. Again, to its stack MFD instruction, we use the exclamation suffix to use the base register auto update feature. For example, in this case, we set R1 is equal to address of SP, R2 is equal to address of SP plus 4. So R3 will have whatever is stored in SP plus 8. The LDMFD instruction also has a variant that does not update the base register. We simply need to delete the exclamation suffix after base register. Okay, let me see. Write a function in C and implement it in ARM assembly to compute x to the power of n when x and n are natural numbers. Assume that x is passed through R0, n through R1, and the return value is passed back to the original program via R0. Answer: n is 0, return 1. Int y is equal to x times power x n minus 1, return y. Okay, I understand what they're doing. So it will be like x times x times x times x times x. Compare R1 to 0. So n is stored in R1, right? X is stored in R0. If x is 1, then we just move if equal 1. Okay, I see. So we compare R1 and R0. If they're equal, then we move 1 to R0. Then branch if they're equal to the calling function. So STM FD SP pointer XP exclamation mark R4 LR. So what is an R4? Save R4 and LR. What is an R4 though? Nothing. Move R4 R0, save X in R4. subtract R1 with 1. Branch to power multiply. Um, okay, so you're multiplying x with x. Then load R4 PC. Restore R4 and it run. Okay, I still don't understand this STMFD and LDMFD. Couldn't this be implemented simply with the branch instructions? How much is left? Okay. This is the last part. In coding the instruction set, let us see how to convert ARM assembly instruction to a sequence of zeros and ones. Each ARM instruction is represented using 32 bits. You need to encode the instruction type, values of conditional fields, register numbers, and immediate operands using these 32 bits only. Let us take a look at the generic format of the ARM instruction. For every instruction, we need to initially encode at least two pieces of information: conditional code, the format of the instruction. So table 4.0 defines 15 conditions on each instruction. It will take 4 bits to represent this information. ARM has 4 types of instruction: data processing, load store, branch, miscellaneous. You need 2 bits to represent this information. These bits determine the type of instruction. So the condition code over here, and then the type of instruction is here. The type field is equal to 00 for data processing instructions. The rest of the 26 bits need to contain the instruction type, special conditions, and register. Figure 4.5 shows the format for data processing instructions, condition type, opcode. What is this S? Source register, destination register, and shifter operand. Shouldn't these two be switched? The 26th bit is called the I bit, similar to the I bit in simple RISC. If it is set to 1, then the second operand is an immediate, otherwise it is a register. Since ARM has 16 data processing instructions, we require 4 bits to represent them. This information is saved in bits 22 to 25. 21st bit saves the S bit. If it is turned on, then the instruction will set the CPSR. The rest of the 20 bits save the input and output operands. Since ARM has 16 registers, we require 4 bits to encode a register, bits 17 to 20. Okay, these. Save the identifier of the first input bit operand, RS, which needs to be a register. It's 13 to 16. These ones. Save the identifier with the destination register. Shouldn't these two be flipped? Bits 1 to 12 are used to save the immediate value on the shifter operand. Let us see how to make the best use of these 12 bits. Or suppose 32-bit immediate values. But this is 1 to 12. Oh, unless. No, wait. 32-bit immediate values. However, we observe that we have only 12 bits to encode them. Hence, we cannot possibly encode all to the power of 32 possible values. We need to choose a meaningful subset of them. The idea is to encode a subset of 32-bit values using 12 bits. The hardware is expected to decode these 12 bits and expand them to 32 bits while processing the instruction. Now, 12 bits is rather unwieldy value. Neither is it 1 or 2 bytes. Hence, it is necessary to come up with a very ingenious solution. The idea is to split 12 bits into two parts, a 4-bit constant and an 8-bit payload. Why is the constant called rot? Let the actual number that is encoded in these 12 bits be n. If n is equal to payload, rotate right 2 times the constant. The actual number n is obtained by rotating the payload by 2 times. 3 times the value in the rot field. Let us now try to understand the logic of doing so. The final number n is a 32-bit value. A naive solution would have been to use the 12 bits to specify the least significant bits of n. The higher order bits could be 0. However, programmers tend to access data and memory in terms of bytes. Hence, 1.5 byte is of no use to us. Better solution is to have a 1 byte payload and place it in any location in the 32-bit field. The rest of the 4 bits are used for this purpose. They can encode a number from 0 to 15. Young processor doubles this value to consider all even numbers 0 and 30. It rotates the payload by this amount. The advantage of doing so is that it is possible to encode a wider set of numbers. For all of these numbers, there are 8 bits that correspond to the payload, and the rest of the 24 bits are all zeros. Rot bits just determine which 8 bits in the 32-bit field are occupied by the payload. Let us consider a set of examples. So encode the decimal number 42 to A. There's no right rotation involved, hence the immediate field is 0 to A. Now encode this number. The number is obtained by right rotating to A by 8 places. Note that we need to right rotate by 4 places to move a hex decimal by 1 position. We need to now divide 8 by 2 to get 4. Thus, the encoded format is 4 to A. Hold on. So, payload is 8 and 4. 1, 2, 3, 4. 1, 2, 3, 4. So 1 byte payload. This is the payload. Place it in any location in the 32-bit field. The rest of the 4 bits are used for this purpose. They can encode a number from 0 to 15. Payload. Okay. We want to store this value. The first step is to count the number of right rotations. We observe that the number has been rotated to the right 24 positions. We now need to proceed 24 by 2 to obtain 12. Thus, the encoding is C28. Okay, so if this goes to the right 4 times, it will end up like this, right? No, 8 times. Right? No, 4 places. So Melanie, this has gone right 12 times. Okay, for this, the first part is to figure out the payload. The payload is 10110111 in binary. This is equal to B7. The next step is to figure out the rotation. Let us simplify the task by observing that right rotating by n places is the same as left rotating by 32 minus n places. Let us concentrate on C00. It is equal to this in binary. The rightmost one is the 11th position. It is moved 10 position. Move 10 position from the first position. Thus, the number has been rotated to the left by 10 places. The reader needs to understand that this encoding is supposed to be done by the assembler or the compiler. The user simply needs to use those values in her assembly code that can be encoded as an ARM immediate. Okay. However, all assemblers are not smart enough to okay, wait, what? Payload, a number like -1 cannot be encoded as an ARM immediate. It is this. The payload is greater than 8 bits, ideally an instruction of the form add R1 minus 1 is wrong. Some assemblers will try to fix the problem by changing the instruction to sub R1 R11. However, all assemblers are not smart enough to figure this out. If the user wishes to use a value that cannot be encoded in ARM 12-bit format, then the user needs to do it byte by byte in a register and use the register as an operand. Encoding the shifter operand. If 10 bits to encode the shifter operand. A shifter operand is of the form RT. 00011011. So why are we using 4? Shouldn't we just use 2 bits for this? First 4 bits encode the ID of the register RT. Okay. The first 4 bits are for the register. Register takes 4 bits. The next bit determines the nature of the shift argument. Immediate or register. If it is 0, then the argument is an immediate. Otherwise, it is a register. Bit 6 and 7 specify the type of the register. Okay, they specify the type. Yes, shifting by an immediate value. Then bits 8 and 12 specify a 32-bit value called a shift immediate. Otherwise, we are shifting by a value in a register. Then bits 9 to 12 specify the ID of the register. Let us consider an instruction of the form add R3, R1, R2. In this case, the second operand is R2. Then think of R2 as actually a shifter operand where it is being left shifted by 0. Hence, to encode, we need to set the shift type to LS. L set the argument to immediate 0 and set the shift immediate to 0. We thus see that specifying a register as a second argument is easy. It's a special case of a shifter operand, and we just need to set bits 5 to 12 as 0. Okay, load store instructions. Simple load store instruction can be represented as LDR, SDR, RD. Okay, wait. I need to. Semantics of the bit is I, P, U, B, W, L. Wait. Condition, type, condition, type. Okay, if it's a load or store, the I bit reserves semantics as compared to the case of data processing instruction. So I means the last 12 bit represents immediate. 1 means last 12 bits represent a shifter operand. P post index or pre index. U subtract offset from base, add offset to base. B transfer word, transfer byte. W do not use pre or post addressing. Then L store to memory or load from memory. Okay. These 6 bits capture all the different variants of the load and store instructions. The rest of the format is the same as data processing instruction other than the encoding of immediates. Immediates in memory instructions do not follow the ROT-less payload format. The 12-bit immediate feed represents an unsigned number between 0 to 4096. What is the necessity of having a U bit? Negative numbers such as -4 or -8 cannot be represented in ARM's 12-bit format for specifying offsets in memory instructions. However, we might need to use addresses with a negative displacement, especially when they are relative to the frame pointer or the stack pointer. The U bit allows us to represent immediate such as -4 or +4. Okay, branch instructions. So branch B and the branch and link instructions. If L bit is equal to 1, then the instructions branch link, otherwise it is just branch. The instruction contains a 24-bit signed offset. The ARM processor first shifts the offset by 2 bits. This is because each instruction is 32 bits or 4 bytes long. And additionally, the hardware expects instructions to be stored at 4-byte boundary. Therefore, the starting address of each instruction will contain 2 zeros in its 2 least significant positions. Hence, there is no necessity to waste 2 bits in the encoding for saving these 2 zeros. The next step is to extend the sign of this shifted offset to 32 bits. Lastly, the hardware computes the branch target by adding the shifted and sign extended offset to the PC plus 8 bytes. The interesting thing to note is that we are adding the sign extended shifted offset to PC plus 8, not the PC. We should see in chapter 10 that the reason for doing this is to simplify the hardware. Format for branches is different from the format used to encode data transfer and data processing instruction. This is because more bits are used to encode the displacement. We had followed a similar approach in Simple RISC also. However, we need to know that having a new format is not a very bad thing if it is simple as is the case for a branch. Now next is the summary. I've been streaming for quite a while, so I will just end it here. And there have been like multiple fluctuations throughout my stream. I will just end the stream here, and yeah. See you guys next time then. Bye.